doesn't work, then that's too bad. Okay, all right. So we will start with the quiz question from quiz 1, and that is the question about removing ones from a string. So this is quiz 1, question 12. All right, so you have a string. So say something like this. Something like this, and available moves are change a 1 to a 0, or 2 consecutive ones to 2 consecutive zeros. Okay, so that is the idea. That's the game that we were playing, and the person without a move loses. Okay, all right. So the main thing to observe here is, so we're trying to find numbers and winning moves. So the main thing to observe here is that you can essentially break this in terms of blocks of ones. Right? So you can just separate them into blocks of ones, and then that becomes different games like this. Okay, so then all you have to do is deal with the numbers of individual blocks of ones. Okay, all right. So what happens here is that you would try to find the number of these one by one. So if you look at the game of 1, there is only one option, which is going to 0. 0 is just star 0. So the max of 0 is just 1. So this is equivalent to star 1. Okay. 2 ones have a few more options, but there are some symmetry involved. So you can remove 1 1, and this would just be 1 zeros. Well, there will be a string of 1 1. So this is star 1, or you can just bring it, both of them, down to 0 0, and this one is star 0. Okay. There's another option of 0 1, but it's essentially the same as 1 0. So we will say this is the max of 0 and 1, and that is 2. Okay, so this is equivalent to star 2. Okay, all right. For 3, there are a couple more cases. So you can either remove 1 1 here, or you can remove 1 1 in the middle, or 2 1s on the end, and the rest are symmetric. Okay, so the rest are symmetric. All right. And the first one is just star 2, because that's 2. The second one is star 1 plus star 1, so that is star 0. And the third one is star 1. Okay, so you have the 2, the 1, and the 0. So we have the max of 0, 1, and 2. So that is 3. So this is equivalent to star 3. Okay. All right. So at this point, you might say, well, there must be a pattern, right? So 4 ones must be star 4, 5 ones must be star 5, but it's not the case. All right, so let's look at 4 ones. If you remove 1 1 here, there are 2 possible cases without with symmetry: 0 1 1 1 and 0 and 1 0 1 1. So these are the 2 possible cases for removing 1 1. Okay. The 3 ones are just star 3, okay, because we have that from above. And 1 plus 1 and 2 is star 1 plus star 2, and that is just star 3. Okay. All right. But and then there is the thing about removing 2 ones. So either removing from the beginning or the middle. Okay. All right, and this one is just star 2, because there's just a length 2, and this one is star 1 plus star 1, which is star 0. Okay, so we're looking at the max of 3, 3, 2, and 0. In this case, it is 1. Okay, so with 4 ones, the number is 1. Okay, all right. So, what we will do then is we look at the original game here, which is, well, this is just something I made up randomly, but it should work the same. So we have 3, 2, 4, 1, 2. All right, so the 2's will cancel out, so we get 1, 3, and 4. Okay, so for the original string is equivalent to 1, 3, and 4. Is that a good idea? I'm not sure. So 1 is star 1, 3 is star 3, and 4 is star 1. So we get star 3, and that is the number for this game. Okay, so this is, in this particular string, which is not the same as the one you have on your quiz, this one is star 3. Okay, all right. And if we're looking for a winning move, right, so if we're looking for a winning move here, then what we will be doing is take this star 3 and say, what does that mean for this named game? Well, technically 1 and 1 cancels out, so we're moving on star 3, and we're trying to move star 3 to star 0. Okay, so then you look at star 3, the 1, 1, 1, and try to move to star 0. You move to 1, 0, 1. Right, so the winning move is to change the 1, 1, 1 to 1, 0, 1 in the original string. Okay, and that is how you find the numbers and the winning moves for this game. All right, good. All right, so that's the first part done. Oops. Okay, so are there any questions you have about this? All right, okay, so I can now move on to the second part. Well, that only took 7 minutes, not too bad. Okay, so we can move on to the next part. All right, oops. All right, so for the next part, I will talk about the second price auction and why why bidding your own valuation is a weekly dominating strategy. Okay, so second price auction. Okay. All right. So just to review what second price auction does, you have one item to sell, and all buyers have a valuation of this item. Let's say VI. So this is what they think this item is worth, and what they will do is try to bid a value to the seller. Okay. Okay, and the seller is going to look at all the bids and say highest bid. The person who bid the highest wins. Okay, so the highest bidder wins, but they don't pay the price of what they bid. Instead, they will pay the second bid price, second highest bid. Okay. All right, so that is the second price auction. You have an item and you have some bids coming from the buyers, and the second person, the person who bids the highest will win, but they don't pay what they bid. Instead, they will pay the second highest bid. Right. So if you have so if you have people bid 30, 70, 90, 60, 120, then the person who bids this one, the 120, wins. Okay, so this one wins, and instead of paying 120, they pay the second highest price, which is 90. Okay, so that is the second price auction. Okay, and the utility for a player is fairly simple. Right? If you don't win, then you have zero utility. Right? So it is 0 if you don't win. Okay. Right. But if you do win, then your utility will be what you pay, what you value the item minus your what you pay, right? So it will be VI minus the second highest value, second price, if you win. Okay, so that is the utility for a player. Okay, all right. So the nice thing about the second price auction is you don't need to think much about strategy in terms of bidding, right? So you don't have to worry about are you going to overbid if you're going to underbid. All you have to do is you bid what you value the item at, right? So you don't need to care about how the other people are bidding. All you need to care is what you are bidding is. If you just bid your valuation, then that should be the best possible. That will give you the best possible outcome, and that should be a Nash equilibrium as well. Okay. All right. So the theorem we had was so a player I bidding VI. So that means that their bid BI is equal to VI. Weakly dominate is a weakly dominating strategy. Right, so if you just bid what you think the item is worth, then that is the best. That is going to be better, equal or better than what you would have done otherwise. Okay, so you don't need to think about what you want to bid. You just bid what you think it's worth to you. Okay. All right. So I will go over the proof of this theorem very quickly. I'm not going to go through all the details because that is a long theorem, but I'll give you the outline of the idea of the theorem just to give you a sense of what that means. Okay, but before we do that, we need to say what weakly dominating means, right? So weakly dominating. Okay, so weakly dominating means that regardless of what the other players play, there's no reason to switch to another strategy, right? So regardless of how others play, utility of playing the valuation VI is maximized. So larger than or equal to utility for playing other bids. Okay, so regardless of how the others play, the utility of playing just your valuation should be the largest possible. Okay, it doesn't matter what the others play. So you fix the other players' strategies. Then you try to compare the strategy of playing your valuation versus playing not your valuation. Okay, so the utility should either be the same or it should go down. Okay, but there's one more thing to weakly dominating. Not only is it the best possible way of playing the game, but also there's a situation where your utility actually strictly increases or strictly decreases if you switch. Okay, right. So also there is some situation where this utility is strictly greater than another strategy. Okay, so there is some way of other players playing their strategy, where if I swap my utility or swap my strategy to something else, my utility actually decreases. Okay, so we don't always get the same utility regardless of what happens, right? So there is some case where the utility does decrease, right? So that is a requirement for weakly dominating. Okay, right, so the definition from the beginning here, where the utility is maximized, this doesn't prevent us from saying, well, the utility is always the same, so therefore it is maximized. So that's why we need a second definition here, where we say that we must have some situation where this utility will actually decrease if we switch to a different strategy. Okay. All right, so that is the theorem and what weakly dominating means and what second auction means. Do you guys have any questions before I move on? All right. Okay. So now I'll briefly go over the proof of this theorem, or how we prove this theorem. All right. So outline of oops, that's not the right thing. So outline of proof. Okay. So I guess I could bring up the proof on that week. Right. So where is that proof? Must be the last lecture, right? All right, okay. So yeah, so this was our proof, and it was a very long proof. But all the things are, I'll give you the ideas for all of them, and then I'll write down the ideas in the other notes. Okay. So the first part of the proof is showing that bidding. Oops, it's a little bit slow. So the first part of the proof is showing that bidding VI. So given other players playing B minus I, bidding VI is always greater than or equal to bidding anything else. Right. So that is the first part. Right. Bidding VI is always greater than or equal to bidding anything else. Okay, so that's what this inequality means. Okay, so we fix the other players' strategies, and we will say, let's look at the utility of playing my valuation versus playing anything else. Okay, and there are two cases here, right? So the two cases here are either my bid is a winning bid, or my bid is a losing bid. Right, so those are the two cases, right? So either my bid is winning, in which case we will decide about, so suppose VI is winning, so then we have to decide what could BI here be, right? So it could be higher or it could be lower, right? So if you're winning and then we bid anything higher, then nothing really changes. We are still winning and we still pay the same price. Utility doesn't change. Okay. But if we are winning, but the second, but our bid is lower, at some point, so this is where this diagram comes in. Right? So if you bid something less than what you value the item, at some point, we might lose when we go below the second bid, a second highest price, in which case our utility actually decreases. Okay, so either is the utility are the same or the utility decreases. So that's why bidding your valuation would be the best when you are a winning bid. Okay. So that is what the first part is saying, right? So if it's a winning bid, then we look at what happens, right? So the utility of the player is the same if it is at least the second highest bid. Okay. But if it becomes a losing bid, then we lose utility. Okay, so bidding VI is the best possible. Okay, all right. Was that too quick? Is that okay? Any questions? Okay, so I'll just write that down. First part one. So we fix the other player's strategies, and we try to show that playing VI is better or equal. Then that's a bad sentence. So it's better than playing anything else. Right, so we're going to say BI is anything else. Okay. And then we had the two cases, either I think it is BI greater than the second highest bid, in which case utility nothing changes, utility is the same, or BI is less than second highest bid, in which case utility actually decreases. Okay. And then there is the annoying part about what happens with equality case, and we'll just ignore that case for now. Okay. So that is the first part. You fix the other player's strategy, and you want to show that playing your valuation is the best possible. Okay, so that is the first part of the proof. Right. So that is completing the first objective of showing it's weakly dominating. Okay. All right. All right, so that was the first part of the proof. And so in both cases, oops. Oh, I can't undo. Why can't I undo? Oh, this froze. Yeah. So in both cases, bidding VI will give the highest possible utility among all possible bids of player I. All right. So we still need the second part. So that is, there is some situation where our utility actually decreases. Okay, so we need to manufacture some possibility where the utility decreases. Okay, given that the other players do not change their strategy. Okay, so that is I need to do that for all possible other bids, right? So if you for all possible other bids, I need to show that there is some situation where the utility actually decreases. Okay, so I need to say for BI equals to something, I need to find some strategy set from the other players so that the utility will actually decrease. Okay. All right. So the first part is, suppose that our bid is actually lower than our valuation. So BI is strictly less than VI. Okay. And the situation we're manufacturing is, let's look at the range between BI and VI and pick some number that is strictly between them. Right? So we pick some number that is strictly between them. We call it K. Okay. And the situation we are making is that all the other players will bid K. Right? So all the other players bid K. Okay. All right. Okay, so if all the other players bid K, okay, and we have to compare the utility of playing VI versus playing BI, which is less than VI. Okay, right. So all the other players will bid k, which is between bi and vi. Bi is what we are supposed to be bidding in this imaginary case. Okay, all right. All right. So the utility when vi is played, right? When vi is played, it is the highest possible bid among all the players. So it will win, and it will pay a certain cost, which is k. So that means the utility is positive. Okay. All right. But if we bid bi instead, then we don't win, and our utility is 0. Okay. So the utility actually does decrease when we play something other than vi. Right, so in this situation here, the utility does decrease in some way. Okay. All right. Okay, so that is the first subcase. The second subcase is when you have bi, if you bid higher than your utility. And the question is, can you actually lose utility by doing so? Okay. And it's a similar case, right? So you look at your valuation and you see that you bid higher and you pick a number that is between the two. Okay. And we say, suppose that all the other players play this bid. Okay. Okay. All right. So then we have to compare the utility of playing the valuation, the best possible, the good bid versus the higher bid. Okay, it's very similar. If you bid vi, you don't win, so the utility is 0. If you bid bi, however, you do win, but you pay the second price, which is k, which is strictly greater than your valuation vi. So your utility is actually negative. You pay more than what you value the item at. Okay. So in this situation, your utility also goes down when played against this situation, when you play a different bid. Okay. All right, so that is the second part. You're trying to find a situation where your utility does go down. Okay. All right, good. Is that okay? Any questions? All right. All right, so I'll write down the outline here. So part 2, we're going to say for each bid, bi not equal to the valuation, find a situation where bidding bi is strictly worse than bidding vi. Okay, so for each bid other than your valuation vi, you find a situation where bidding bi is actually worse than bidding vi. So that is the second part. Okay, and the first case is when bi is less than vi. Then we will pick the other players to all be k, where k is between the two. Okay, and the utility of vi is positive, and the utility of bi is 0, so it strictly decreases. Okay. All right. And the second case is when bi is strictly greater than vi. So you bid higher than your evaluation of the item. That's never a good idea. So you pick the situation b minus I to all be the same one, k, where k is still between the two numbers. Okay. And in this case, utility of bidding VI is 0, and the utility of bidding BI is strictly less than 0. So it still decreases. Okay, and that is how the outline of the proof works. Right, so you are trying to show that playing your valuation is always better. It always gives you the maximum possible utility. That is part 1. And part 2, you need to find some situation where it actually does decrease, right, for any other bids. Okay, so that is how you prove weakly dominating. Okay, all right, good. Any questions? I do have another thing to go through before I can go to quiz question. Yeah. If we have time at the end, then we can do that. Yeah. Okay. Any questions about this part? Okay. All right. Okay, so we will go to our last part, which is somebody requested to talk about rock, paper, scissors. Okay. Right, so rock, paper, scissors is a very simple game. If you just show rock, paper, or scissors. If you win, you get utility 1. If you tie, you get utility 0. And if you lose, you get utility -1. So let's give you the payoff table here. Okay, so that's how you would play rock, paper, scissors, right? So you play rock, and the other player plays paper. Then you lose, so you get -1, and the other player gets 1. Okay, so that is rock, paper, scissors. Okay. And the idea is we will try to find a Nash equilibrium in this game, but we also want to show that that is the only Nash equilibrium. Okay, so in this case, we need to look at the mixed Nash equilibrium. So we are looking at the probability distribution over our 3 strategies. Okay, so we want to show that the only Nash equilibrium is each player plays 1/3, 1/3, 1/3. Okay, so basically the idea is that the best way to play rock, paper, scissors is to play randomly. Okay, so you play each one with the same probability. Okay, and we want to show that this is the only possible Nash equilibrium for this game. Okay, and there are no other Nash equilibriums. Okay, all right. Now, so a couple of things we need to do for this. First of all, we need to know how to calculate expected utility for a player playing a game, playing a strategy. But also, we need to use the support characterization to show that it is best possible. Okay. All right. So let's just write down support characterization quickly. So support characterization. Okay. All right. So support characterization comes from the linear programming formulation of the mixed Nash equilibrium, the best response function. And the idea is that if for a strategy to be in the best response function, against another strategy. I don't remember what I did against the remaining player strategy. All the non-zero, all the positive probabilities must correspond to a pure strategy, so strategies without probabilities that give the highest utility. Okay, so if I play a strategy, which is a probability distribution over all of my pure strategies, if I play any positive probability in my strategy, that means that that strategy has to be a pure strategy that has the highest possible utility against the other players. Okay, so that is the way. So that is support characterization, and this can be used to prove that some Nash equilibrium is not possible. Okay. All right. Okay. So what we will do here is to show. So we want to show that this is the only Nash equilibrium for our game. And apparently, all three of these are positive. Okay. So essentially, what we need to show is that the only way for this to work is that playing any one of these three strategies should give you the highest utility, meaning they have the same utility. Okay. All right. Okay. All right. So now, because I don't have much time, so I will just give you an outline of how this proof would work. Right. So outlining a proof. Okay. All right. So we can try to show that it is impossible to play a pure strategy, right? So it is impossible to play just rock or just paper or just scissors, okay? And that should be fairly easy to see, right? So if you have a strategy where you just play rock, the other player will just play paper, and then you would have a reason to deviate from your strategy. All right, so that is the easy case, though. So the first one is if you impossible. It is impossible for NE, for a Nash equilibrium, to have a pure strategy. Right, so if a player plays a pure strategy, then it is impossible to have a Nash equilibrium. You will always be able to switch to get a better utility. Okay. And the second part is to show that it's impossible to have a Nash equilibrium where when you spread between two strategies, right? So impossible when we spread between only two strategies. Okay. Okay. All right. So, for example, if I play rock and paper, right? So if I play rock and paper, then it is basically easier if the opponent just plays paper, right? So if I only play rock and paper, then the other player will just play paper, so they will either tie or win. Okay, and then that goes back to having impossible to have a pure strategy. Okay, so that is the second part. It is impossible when we spread between only two strategies. Okay, so if you want to prove this, then you will say something like so let x1 be, say, p1 minus p and 0, you calculate the utility of player 2 of playing rock, paper, and scissors. Okay, and show that there is a contradiction somewhere in there. And the contradiction would probably be that playing paper would be the best strategy, right? So the contradiction would be U2. Paper. Okay. All right. So that is the second step in the proof, that there is only one possible Nash equilibrium. Right. So the third step is to say that we had to assume that all three are used. So x1 is something like P, let's say P1, Q1, 1 minus P1 minus Q1, and x2 is equal to, let's say P2, Q2, 1 minus P2 minus Q2. Okay. All right. So we have to assume that all three pure strategies are played. You're distributing over all three of them. Right. So then you will need to calculate the utility. So for example, if I calculate the utility from player 1, playing rock against x2 is equal to something. And utility of playing paper is something. Utility of playing scissors is something. And they must be equal. Right, so this is by the support characterization. They all have to have maximum utility. So these must be equal. Okay, and similar for player 2. Okay. And then you will find that you will end with all of them equals to 1/3. Right, so that's how you say that there is only one possible strategy of playing rock, paper, scissors. You distribute all, equally over all three strategies. Okay. That is a very bare bones outline. Hopefully you will be able to figure out the details of how to prove this. And you can ask me on Piazza if you need, or office hours if you need more guidance on how to prove this. Okay. Okay, any questions? All right. Okay. So it's almost 9:50. Yeah, if you want to leave, that's fine. Hopefully you have a great week, and I'll see you next week. But let me answer your question about the quiz then. Oh yeah, that's a tricky one. Yeah. Yes. Okay, so why is impartial game not the same as NIM game? All right, so even though they look the same, and so here is a couple of reasons for why winning impartial games might not have odd number of winning moves. Okay. All right. Okay. So first reason is that in NIM there is only one way to get to 0. only one way to get a pile to 0, start 0. Right, so in NIM, it's a very simple game, right? So if you have a pile, if you want to move to 0, you just remove all the pile. Or if you want to move to another stack, or star 0, or another star k, for example. So there's only one way to get to a pile of 0. However, in other impartial games, there might be multiple ways of getting there. And so this might happen in multiple ways in other impartial games. Okay, so I'll give you an example. So the example from the last tutorial, right? So it's the White-Hoff game, right? So the White-Hoff game, you take your queen, you either move to the left, down, or diagonally down. Okay, and we had this chart. We had this chart here. Okay, so here's the interesting part. If you look at this star, this location here. So if I have 3, 2, and I get this location here. To move to 0, I can either move here or I move here. So that's 2 ways of getting to 0. So in this case, there are actually even number of winning moves for this particular game. Yeah. So that is the sneaky part on that. And most of people got that wrong as well. So, but there's also a second way that we might have more winning moves, and that is that in NIM, the numbers always go down. Go down for a pile, right? But we may increase the number of an impartial game to get a losing game. Okay. Right, exactly. So this might be a little bit harder to come up with an example on the spot. But yeah, I've seen something like this before, right? So even in the White-Hoff game, where if you have, say, a 2 here, and if it is possible to move to a 5, for example, then you might move to 5, right? So, for example, if you have star 2 plus star 3, so if you have this 2, anyway, there is some. So in some situations, it is possible to get a losing game by moving upwards to 5, for example. Oh yeah. So for example, if I say, let's take this game plus the NIM game of star 5. So I can get a losing game by moving 2 to star 5. So then it becomes star 5 plus star 5, so it becomes a losing game. Yeah. So that's why poker NIM is kind of the thing in in that part of the course, right? Yeah. Okay, so those are the 2 reasons that I can come up with for why this is weird. Yeah. All right, sounds good. All right. Okay. Any other questions? All right. Okay. Sorry about going over time and the technical troubles earlier. Thank you for coming here today, and have a great week. And hopefully I'll see you next Monday. All right. No problem. I think I'll stop this.